Okay, let's give you guys some practice now. So let's say you're trying to film a shuttle launch. This here, you are here with your camera. The shuttle here is always traveling at 300 meters per second in the vertical direction. So what that means is if you call this h, the height here. So as far as the rocket is concerned, dh by dt is 300. Okay. The question is, uh, what how when the rocket is at 500 meters above the ground, how fast should you program your camera to rotate? Meaning that as the rocket travels vertically upwards, your camera will launch. Sorry, your camera will rotate in this direction here. So theta increases as the rocket gets higher and higher. The question is, at this precise moment in time, when it's 500 meters above the ground, how fast is the rotation here? So basically, what I'm asking you is to find out d theta by dt at this precise moment in time when the rocket is 500 meters above the ground. Okay, so press pause and have a go. Okay, so the trick to doing this is to find out the connector, if you like. There's something that connects everything together. There's something that connects the height and theta together. In this case, it is the tan that connects everything. Okay, so hang on. So it's this thing that connects everything. So h here is the height above the ground of the rocket. Okay, so this here is h. So what we know is we do know dh by dt equals 300. Okay, that's this thing here, and the thing that connects everything is really tan. So hang on. So tan theta equals h over 1000 here. Okay, so from this here we can use implicit differentiation. But before you do that, identify well you are we want to know we are varying the situation varies with time. So what that means is looking at this here. So you've got your h here, you've got your theta here. Okay, so as time moves on, h is really a function of time. As time moves on, theta here is a function of time. As time moves on, this is not a function of time. This is you here with your camera will always be 1000 meters away from the launch site. Okay, so this is a function of time. This is a function of time. Now, hang on. So when you want to solve this, try and identify your connector. What is the thing that connects everything together? It is your tan. It is it is tan that connects everything. So now bear in mind that that theta is a function of time. Okay, theta is a function of time, and h here is a function of time. So when you differentiate it, bear that in mind. So hang on. So from here, differentiate it. Now let's use implicit differentiation. So bear in mind that that theta is a function of time, h is a function of time. So when you differentiate this, it will give you this. Okay, so remember, when you differentiate tan of theta, it does actually give you this. And if you can't remember, then think of tan. Well, search one of the earlier videos. When you differentiate this, it does give you this. Okay, now because theta is a function of time, then you've got to stick d theta by dt in here. Okay, so now so when you differentiate this side, it will give you this. Now when it comes to this, imagine it as 1 over 1000 h. So when you differentiate this, it will just become this. But because h is a function of time, you've got to stick dh by dt. Okay, so from here we will get to here. And then now once you are here, think about the precise moment at that specific time. Okay, think about the precise moment in time when the shuttle is exactly 500 meters above the ground. Okay, so when the shuttle is exactly 500 meters above the ground, tan theta will be, well, tan theta will be this, because 500 over 1000 is a half. And then when this thing here, when you square it, it will give you a quarter. Okay, so this 10 squared theta here is actually a quarter, so we can put this in here. So this becomes 1 plus a quarter. Okay, this is what we want to know: d theta by dt. Dh by dt is the speed of the shuttle at that precise moment in time. Okay, so we know dh by dt, so we can put that into here. We can hang on, let me think. This thing here will go into here. Okay, and oh, this is rubbish. Okay, we are trying to find out the theta by dt. Okay, sorry. So this thing here is rubbish. So we do, at this precise moment in time, we know that tan theta equals a half. So from that we know tan squared. So we can put that into here. So that will then take us to this. Okay, because hang on, bear with me. So this tan squared here goes into here. 1 plus a quarter is 5 over 4. That gives you 5 over 4 here. The d theta by dt is what we want to find out. And on the other side we've got this. Well, we know this here is 300, so we can put this into here. Okay, so 300 over 1000. This will cancel out here, and then basically you just want to rearrange it to make the theta by dt get d theta by dt on its own, blah blah, it equals this. Okay, so d theta by dt is given by this. So that this is how fast your camera should be rotating per second. So what that means is this. Hang on. Let's say this is your rocket here, 500 meters above the ground. You're 1,000 meters away. So if you think about it, from here to here it's pi radians. Okay, so 1 radian would be, well, pi is roughly 3 radians roughly. So 1 radian is probably, this here is probably 1 radian. But at this precise moment in time, you see, when at this precise moment in time, the camera should be rotating at 6 over 25 radians per second. So that's what this means here. Okay.